This is for the tokamak that they have on the USU campus, and I have skipped a lot many details, and I'll possibly have to skip even more, but that's okay. So here's what I wanted to talk about is like introducing the machine, the operating characteristics, estimating the position, how to go about modeling or controlling it, and then some hardware emulation plans that we have and how we plan to do it. So for those of you who do not know what the tokamak is, this is just how it looks like. It's nothing but a transformer which has a primary coil, which is the core, and then there is this steel tube inside which there is a very low pressure gas, which is the pressure inside is of the level of high vacuum. So you pump current in through this coil, and that introduces a field in this winding, and it makes the plasma current flow. And you also have currents in these colloidal fields, which gives which gives rise to a current and field in this direction. So the resultant field that you get is this red line, which is a helix. It's not clearly shown here, but you have a helical field which confines the plasma in that tube, and this is a magnetic confinement device. And the only reason people look at this right now from the research point of view, because this is the only device which of the fusion devices, this is the one which is the most promising to give you power in future. So
they call this desktop sound.
Yeah.
Okay.
So
heat fusion.
That's the name of the machine that I have data from, and these are the parameters. The major radius is the radius of the torus, the minor radius is the radius of the pipe, and these are the other parameters. It's called Star 1M because it's on kind of a lease from the University of Saskatchewan to the Utah State University, so it's not our machine. And just to get started, these are the normal operating characteristics or the input parameters. Like you have several fields on that machine. There are like 7 magnetic fields, and each one of them have to be fired at a specific time with the accuracy of a millisecond, and they have to have a specific shape if you expect any plasma discharge at all. So if you see like these times, 1.5 milliseconds, 3.8 milliseconds, these are not coincidental, or these are not whimsical values. There's a lot of math and formula and physics behind it to do that, and there are dedicated physicists doing that all the time. So if you give such a lot of, if you generate these waveforms on the input, what you get on the output is this. So like this is the plasma current that is established in that steel shell, and that is the voltage of the loop. So if you see that the plasma discharged starts roughly at 3.4 milliseconds, and it is stable only for around 5 milliseconds at the max. 5 milliseconds is the theoretical lifetime that they have estimated, but it is usually lesser than that. It's around 4 milliseconds, and it's only at this top portion, this flat portion here, is when it is actually stable. And because all of this part is when the current is ramping up, there are other fields shutting off or starting up, and you have various MHD instabilities here, and then this part is again decay, and so the data at that part is useless to do what we are doing. So now getting to the part, what I am trying to do is the physics professors here, Dr. Farrell Edwards and Dr. Eric Held, have come up with a new theory which states that if you have to get energy out of this machine, there are many theories, but what they say is if you can pinch the plasma down, or if you can compress it, and you reach a minimum energy state, and when you reach that, it will generate more energy, and that will happen at a far lower temperature than is stated by any other plasma physicists. And they have theoretical results proving it, but this is the effort to make that practically happen. And one of the main requirements for that is for the plasma to be centered in the shell, and that is what is my master's thesis based on, plasma position control. And so my job would basically be to find out a model and a controller which would make the plasma column stay in the center. So this is the setup they have. They have like this is the torus that goes around, and if that represents the plasma, then these red dots represent the magnetic pickup coils that they use to measure position. and then they have a control winding on the top of it. So this red dot represents the plasma, and if it moves, then these pickup coils will pick up a magnetic field, and based on the geometry of the device, we can come up with these formulas. This is pretty basic high school math.
Where
It's
do you
like,
get this from?
this is just basic physics. Like, this is the magnetic field strength at the distance r from due to that current IP, which is the plasma current, and it's related by some factor to the voltage that we get on the pickup coils. The two factors, alpha 0 and alpha I, are such that they are very, very close. They differ only by the third decimal, so we can disregard them. And based on the geometry that I showed here, if you assume that this dot hits one of the walls, like say it's here, then the distance from one of them will be 15 millimeters and the other will be like 85. So based on that, we can calculate what the ratio between the two coils signals voltages will be if the plasma is at the wall. That is how we estimate the position. And the red line is an estimate of the position that you have from. It's an average across six shots, because each shot is different from the previous one, but they are on an average they are kind of the same. They're not identical, but they vary in a bound. So
How many cycles do you make in this 5 milliseconds?
you mean how many
It's the speed of the
Cycles of the
how many